this is a special announcement. We are heading to RSA conference in San Francisco for our 11th years of coverage, April 28, May 1st.
And as always, we're bringing you keynotes, conversations with organizers, speakers, industry leaders, plus the latest insights from the world of cybersecurity.
And we'll reconnect with old friends, meet new ones, and of course, we want you and your company to join us.
We have a few spots left for full sponsorship and our on-location briefings. You can book yours now at itspmagazine.com/RSAC.
We're going.
And you're coming with us.
Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to another episode of Stories from Space. I'm your host, Matt Williams. And today, after much waiting, we're going to be looking at the breakthroughs, discoveries, and unexpected finds brought to us courtesy of the James Webb Space Telescope, the next-generation observatory created by NASA, the European Space Agency, and the Canadian Space Agency. The mission launched on December 25th, 2021, on Christmas Day, no less. Quite the present. And this represented the culmination of decades of planning and preparation, which began in 1996. At the time, the telescope was codenamed the Next Generation Space Telescope, and after multiple delays and cost overruns due to the sheer complexity of the design, it finally made it to space and began capturing the clearest and most detailed images of the universe ever seen. The mission has been identified as a successor to the Hubble Space Telescope, given that it was designed to view objects that were either too old, too distant, or too faint for the venerable Hubble. In addition, Webb is the designated successor to the Spitzer Space Telescope, an infrared telescope that spent years observing the unseen universe, which is to say, the parts of the universe that cannot be viewed in visible light because they're obscured by dust, gas, or brighter objects, or simply too faint. And with its sophisticated mirror and an advanced suite of instruments, astronomers expected that it would be able to make many investigations across multiple fields of astronomy and cosmology, which would include the first galaxies in the universe, forming less than 1 billion years before the Big Bang, studies of red dwarf suns and brown dwarfs, as well as planet-forming debris disks, much like Spitzer, and also the detailed characterization of exoplanets. Specifically, characterization of their atmospheres to determine if they could in fact be habitable. All of this was made possible by a complex gold-coated beryllium primary mirror made up of 18 separate hexagonal mirrors. Add to that a sun shield that prevents the Webb telescope from being overheated by any external heat sources, which would throw off its infrared sensors, and its origami-like design, which allows it to fold up so it's small enough to fit into the payload fairing of a rocket, and then deploy in space, and you've got the most powerful, sensitive, and complex observatory ever deployed. So what has Webb accomplished since it was deployed roughly 3.5 years ago? The list is long, but a few things stand out above the rest. For instance, the discoveries made by Webb have led astronomers and cosmologists to rethink a lot of their previously held notions. This is precisely what Webb was intended to do. By viewing the earliest galaxies in the universe, astronomers hope to get a better idea of everything that occurred during the early universe that led to the universe evolving into what we see today. In addition, Webb was intended to make accurate distance measurements of the most distant observable objects in our universe in the hopes of resolving a major issue that has plagued astronomers since the 1990s, which was originally discovered by the Hubble telescope. And this is known as the Hubble tension. To break that down, first we need to talk about how astronomers measure cosmic distances, which requires several different methods, collectively known as the cosmological distance ladder. The purpose of these distance measurements is to determine the rate at which the cosmos is expanding. As noted in previous episodes, this is known as the Hubble-Lemaitre constant, named after Edwin Hubble and Georges Lemaitre, the two astrophysicists who first noted that the universe was in a state of expansion back in the 1920s and 30s. Prior to the 1990s, astronomers were able to get a clear view and distance measurements for objects up to 4 billion light-years away. But with the deployment of Hubble, that all changed. Initially, Hubble was able to study objects up to 10 billion light-years away. But as time went on, and with the Hubble deep fields, astronomers realized that the rate of cosmic expansion was getting faster over time. As a result of this, obtaining accurate measurements of distant objects became absolutely crucial. And for this, astronomers rely on the cosmological distance ladder. As indicated in our episode about the Hubble tension, this ladder consists of several rungs, each of which involves a different method and a different standard candle, or bright object, to gauge the distance of objects that are farther and farther away from the solar system. For local distances, astronomers use parallax measurements, a technique that has been used since classical antiquity to determine the distance of planets. But in modern astronomy, this technique consists of observing stars that vary in brightness, otherwise known as variable stars. And when viewing Cepheid variables from different points in Earth's orbit, astronomers are able to determine the distance to objects that are between 10,000 and 100,000 light-years away. The next rung of the ladder consists of parallax measurements for Cepheid variables and RR Lyrae variables, an even brighter class of star. These two techniques combined allow astronomers to gauge the distances of local objects within our galaxy, as well as local galaxies, the closest neighbors of the Milky Way. But for the next rung of the ladder, measuring distances up to 1 billion light-years away, astronomers require a much brighter standard candle, to which they turn to Type 1a supernovas. A Type 1a is a type of supernova that occurs in binary systems, where one star is a white dwarf and the other can be anything from a massive star to a smaller white dwarf. The powerful gravity of the white dwarf star will gradually siphon material from the other star, eventually reaching a critical mass, at which point it will ignite and trigger a supernova explosion. Beyond distances of 1 billion light-years, astronomers must rely on redshift measurements. Essentially, redshift describes how, due to the expansion of the universe, light coming from distant sources is shifted towards the red end of the spectrum. To put it another way, the wavelength of the light is elongated by the expansion of space-time itself. And since longer wavelengths correspond to light that is closer to the red end of the spectrum, you get redshift. Therefore, the farther the object is away from Earth, the longer the elongation. And as noted, before the 1990s, observations and redshift measurements were restricted to objects within 4 billion light-years. Hubble managed to change all that by measuring redshift of some of the most distant observable objects that were up to 13 billion light-years away. And given that astronomers, when looking through distant space, are also looking back in time, this meant that these were the first galaxies in the universe that had emerged from the so-called Dark Ages about 13 billion years ago. And this was accompanied by measurements of the cosmic microwave background by NASA's Cosmic Background Explorer, or COBE, and the European Space Agency's Planck mission. As noted before, the CMB refers to the relic radiation emitted shortly after the Big Bang, when neutral hydrogen atoms finished forming, allowing for the free propagation of photons. Given the immense distance that this light has crossed in order to reach us today, it has been redshifted to the point that it is no longer in the visible spectrum and can be seen only in the microwave wavelength. By measuring the redshift of the CMB, astronomers were finally able to constrain the age of the universe at roughly 13.8 billion years. However, when comparing distance measurements on different rungs of the ladder, they noticed a discrepancy. Essentially, the CMB measurements indicated that the Hubble constant was about 68 kilometers per second per megaparsec. In other words, for every million parsecs, the universe is expanding at a rate of 68 kilometers every second. However, measurements of the local universe and local galaxies produced a value of 74 kilometers per second per megaparsec. This came to be known as the Hubble tension. For decades, astronomers looked forward to the day when the next generation space telescope that would become Webb would be deployed to space, would make its own measurements of the distant galaxies in the universe, and hopefully resolve this tension by bringing all the values into harmony. However, Webb's observations confirmed Hubble's original observations, producing the same measurements that were in tension. In an attempt to explain this, astronomers and astrophysicists have been working on various theories. Currently, a leading contender is the idea of early dark energy, which would, according to theory, produce a burst of extra unexpected expansion in the young universe. This energy, they theorize, would then decay faster than other radiation, leaving the late evolution of the universe unchanged. These observations have also led to a controversial theory that the universe may in fact be older than the standard model of cosmology predicts. This theory, argued by Rajendra Gupta in a recent paper, proposes that the universe may be 27 billion years old rather than 13.8. This theory is based in part upon the concept of tired light, a theory first proposed in 1929 by Fritz Zwicky, who suggested that if photons lost energy over time through normal matter collisions as they travel through the universe, that this would cause light from distant objects to appear much redder. However, this theory presents many theoretical problems of its own, and for the time being, the standard model of cosmology remains in place. Another primary objective of the James Webb mission was to witness the formation of the early stars and galaxies, the purpose of which was to fill gaps in our scientific knowledge. Astronomers have a very good idea of what galaxies look like today, based on centuries of observation, and thanks to the Hubble Space Telescope and its successors, they have a good idea of what galaxies looked like roughly 13 billion years ago when they emerged from the so-called cosmic dark ages. This has allowed astronomers to chart the evolution of galaxies over time, but only to a point. By seeing them in their very early stages, astronomers and astrophysicists and cosmologists hoped to test theories about galaxy formation and the role played by supermassive black holes. To break it down, the first galaxies are theorized to have begun formation roughly 380,000 years after the Big Bang. This coincides with the cosmic dark ages, which lasted until about 1 billion years after the Big Bang, and which astronomers can see in visible wavelengths. The dark ages, however, are so called because the universe was permeated by neutral hydrogen. Only two sources of light, aka photons, were visible during this cosmological period that would be accessible to astronomers today. This includes the relic radiation of the cosmic microwave background and those photons that are occasionally released by neutral hydrogen atoms as they were undergoing reionization. This reionization coincided with the formation of the first stars in the universe, known as population 3 stars, to differentiate them from the two subsequent generations of stars, population 2 and 1. Unlike most population 2 and 1 stars, population 3 stars are theorized to have been very massive, very hot, and short-lived, with main sequences that lasted just a few tens of millions of years. They also emitted intense amounts of ultraviolet radiation. This led to the theoretical era of reionization, in which the clouds of neutral hydrogen were reionized and slowly dissipated, By 1 billion years after the Big Bang, the universe became transparent, quote unquote, to modern instruments, which is to say, observable and visible light. Due to the tremendous cosmic distances involved, all the light that existed before the universe became transparent is redshifted to a point that it is only visible in parts of the infrared spectrum, which are very difficult to observe. Enter the James Webb Space Telescope, which relies on advanced optics and infrared instruments, as well as an advanced heat shield that prevents thermal interference. Thanks to this combination, the earliest galaxies that existed during this period, also referred to as cosmic dawn, are now accessible. When astronomers got their first look at these galaxies, they were rather surprised. For one thing, there were far more galaxies in the early universe than the standard model of cosmology predicted. What's more, the galaxies themselves appeared much larger and brighter than expected. In accordance with the standard model, there simply wasn't enough time for this many galaxies to have formed or for them to accumulate as much bright stars as they did. This too has led to some new and interesting theories which attempt to explain this and bring Webb's observations and the standard model of cosmology into agreement. This includes a recent study by the International Cosmic Evolution Early Release Science Survey, known by the abbreviation CEERS. According to the theory they advanced, the brightness that has been observed by astronomers may be an optical illusion. In theory, they argue, supermassive black holes at the center of early galaxies would have rapidly consumed gas, causing friction that caused the gas to produce light and heat. This is similar to what astronomers observe today with quasars, aka quasi-stellar objects, which refers to active galactic nuclei, where the central region of massive galaxies that have powerful supermassive black holes emit tremendous amounts of radiation, causing them to temporarily outshine all the stars in their galactic disks combined. If this theory is correct, the light emitted by all this superheated gas would make these galaxies appear much brighter than their population of stars would suggest, thus creating the illusion that these galaxies had larger stellar populations than models predict. A similar theory has been suggested by the JWST Advanced Deep Extragalactic Survey, or JADES. Their research suggests the universe was much denser during this early period, which prevented early stars from pushing away clouds of gas during their formation. This could, in theory, have led population 3 stars to form more rapidly than their contemporaries, thus allowing galaxies that are larger and more populated to have existed earlier than expected. Which brings us to another major objective of the JWST, which was to observe the seeds of supermassive black holes during the early universe. For decades, astronomers have known that most massive galaxies have a supermassive black hole at their center, and this includes the Milky Way. At the Milky Way's core, there is Sagittarius A. This black hole has a bright accretion disk consisting of gas and dust that has been accelerated to near the speed of light, causing the release of tremendous amounts of energy, and has several stars in its orbit, some of which will eventually be consumed. But, as astronomers use Webb to observe early galaxies, they found that the seeds of supermassive black holes were also larger than standard models predicted. This included EGSY 8P7, a galaxy that existed just 570 million years after the Big Bang. At the center of this young galaxy, astronomers were surprised to see a black hole that is roughly 9 million times the mass of the Sun. Even greater than that was a supermassive black hole at the center of UHZ1, which was observed in 2023 by Webb and the Chandra X-ray Observatory. This galaxy existed when the universe was just 470 million years old, and at its core, a black hole of 40 million solar masses, 10 times the mass of Sagittarius A. What's more, its host galaxy had an estimated mass of only 100 million suns, comparable to the small Magellanic Cloud, the satellite galaxy just outside the Milky Way. The dual observations also indicated that this black hole was not as bright as the more massive black holes that are observed in the present-day universe. A possible theory that has been suggested is that the first supermassive black holes may have been the result of direct collapse, which could, in theory, have given them enough time to grow this massive. In other words, they formed from the collapse of massive clouds of gas, rather than going through the process where gas formed stars, which eventually collapsed to form the first black holes, slowly growing over time by accreting more gas and more stars. Lastly, there are the many finds and breakthroughs that the JWST has allowed for in the field of exoplanet studies. As of the recording of this episode, the current exoplanet census stands at 5,849 confirmed planets, with more than 10,000 candidates awaiting confirmation. With so many exoplanets available for analysis, the trend has begun to shift from the process of discovery to characterization. In other words, the field is transitioning from simply looking for more exoplanets towards getting a closer look at them so we can learn what kind of chemical abundances they have in their atmospheres, which could indicate the existence of life. The JWST has proven itself to be particularly excellent at exoplanet characterization because of two key factors. For one, its large 6.4 meter or 21 foot mirror collects a lot of photons that conventional telescopes cannot. This allows the JWST to observe very dim objects, as well as objects that are very close together. This is very useful when conducting direct imaging studies of exoplanets, where it is able to isolate the faint light being reflected off of a planet, while its onboard coronagraphs are able to block out the light of the parent star. The JWST also has advanced infrared cameras and spectrographs that allow it to break down the light of these dim and distant objects into a spectrum. By analyzing at what wavelengths light is being absorbed and radiated outwards in the atmospheres, it is able to produce spectra. In other words, indications of what chemicals are present. As of the recording of this episode, the JWST has observed 127 planets, 64 of which were gas giants comparable in size and mass to Jupiter or Saturn, while another 38 were Neptune-like planets, and 31 were rocky planets comparable to Earth. The majority of these were observed during what is known as a transit, where a planet passes in front of its star relative to the observer. During these transits, light passing through the exoplanet's atmosphere was observed by Webb, from which spectra was obtained. In 15 cases, Webb obtained spectra directly from exoplanet atmospheres using the direct imaging technique. Of these, perhaps the most impressive was WASP-39b, which Webb observed as part of its early release science program. WASP-39b is a Saturn-sized world, less than a third of Jupiter's mass, located in a system 700 million light-years away. Webb viewed this planet with all of its instruments, which allowed the mission team to cross-validate the results, and revealed a number of interesting things about this gas giant's atmosphere. Among them, unexpected things like water, CO2, and sulfur dioxide. This represented some of the very first data that came from the telescope and showcased the telescope's abilities to characterize exoplanet atmospheres, as well as obtaining data about conditions beneath the upper layers, which could include atmospheric mixing, tidal heating, and chemical interactions. The funny thing is, JWST wasn't designed for this kind of research. Its instruments and its mirrors were mainly fashioned for observing light from the very early and distant universe. However, these same abilities have made it particularly excellent at characterizing exoplanets. When NASA launches the Nancy Grace Roman Space Telescope in 2027, named after the mother of Hubble and Hubble's direct successor, the two will work in tandem. Whereas the Roman Space Telescope will use its advanced imaging capabilities and wide field of view to detect tens of thousands more exoplanets, Webb will conduct follow-up observations in order to characterize them. So far, Webb has not detected any habitable planets, but the science is nevertheless impressive, and it does offer tantalizing clues of what's to come. These are just some of the things that the James Webb Space Telescope will explore and discover as it conducts its 5.5-year primary mission. While the observatory is planned to remain operational for 10 years in total, decommissioning sometime in 2031, Scientists expect that it will last for at least 20 years, and in that time it will be joined by several next-generation telescopes, included the aforementioned Nancy Grace Roman, and also the Habitable Worlds Observatory. This is another accomplishment that the Webb telescope has made since its launch in December of 2021, which is to showcase the abilities of next-generation telescopes and their capacity for investigating the cosmological mysteries that were introduced to us by the venerable Hubble Space Telescope, as well as many cutting-edge ground-based observatories. Astronomers are also looking forward to next-generation ground-based telescopes, which fall into the 30-meter category, which is to say they have primary mirrors measuring 30 meters in diameter or 100 feet. However, that's a subject for another podcast. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
This is a special announcement. We are heading to RSA conference in San Francisco for our 11th years of coverage, April 28, May 1st.
And as always, we're bringing you keynotes, conversations with organizers, speakers, industry leaders, plus the latest insights from the world of cybersecurity.
And we'll reconnect with old friends, meet new ones, and of course, we want you and your company to join us.
We have a few spots left for full sponsorship and our on-location briefings. You can book yours now at itspmagazine.com/RSAC.
We're going.
And you're coming with us.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.